Hey guys, this is Kendall Terry, and we are today looking at sex linkage, which is the first part of this section. Here, looking at how we map out chromosomes and stuff like that. And we've got an experiment from Thomas Hunt Morgan in 1910, in which he looked at a white-eyed fruit fly. He found some mutants, in essence, growing in his fruit flies that he was doing experiments with, and he noticed that there were some white-eyed males in there. So he took white-eyed males and he reproduced them with red-eyed females. And what he noticed is that all the F1s were red eyes, which is exactly what you would expect to see. Then when he let them reproduce into the F2, that's where some things started to get different, though, because he noticed that he had females were all red eyes, whereas the males, half of them were red eyes and half of them were white. That should be white, not female. Oh man, messed up there. All right. So imagine half of them red, half of them white, not female there. Sorry about that in your notes. So then he took one of the F1s and he did a test cross with them. Remember, we've talked about this, that test cross is taking a genotype, a positive or a dominant genotype, and crossing it with the homozygous recessive. He was assuming, because white eye disappeared here, that white must be recessive to red. So he got his white-eyed males back, and he crossed that white-eyed male with one of the F1 females. And he noticed then that he had his females were half red, half white, and his males were half red, half white. So there was a significant result here in looking at the difference between male and female. So what we discovered in this is that apparently there was a chromosome gene located on what we call the sex chromosomes. Remember in the past we talked about this, that males are XY, females are XX. This is the case with mammals and fruit flies. When you get outside of mammals and fruit flies, you get into some different combinations that you can have. For instance, in honeybees, you have the difference between diploid and haploid. Diploid's female, haploid is male. And then there's others. In birds, it's ZZ is female, Z0 is male. I think that might be flipped around the other way, though. So you get different combinations as you look at different organisms. In mammals, we deal with XY is male, XX is female. So if then we look at, for instance, Thomas Morgan's original research, then we say, let's hypothesize that the male has a white-eyed gene on the X. On the Y is just the male genes. That doesn't have any weight here. So if you have the white-eyed gene, then you have the white-eye characteristic. On the female, you've got normal X's. So when you cross these two, you end up with a red-eye female, a red-eye female, a red-eye male, and a red-eye male. All of them are red eyes, and that's exactly what Thomas Hunt Morgan noticed in his experiment as well. Then he allowed the F1s to reproduce, and you get a red-eye female that has the white-eye gene, a normal male. All the males were normal here. When you cross those, you end up with all of the females red eyes, because this red eye is dominant to that white. And the males, you have half of them are red eyes, half of them are white, which is also what Thomas Hunt Morgan discovered in his original research. When you take this example and you do a test cross with it, and you take a white-eyed male and cross it with one of the F1 females right here, one of these, both of them are the same, so one of those, then what you notice is you get a red-eye female and a white-eye female, a red-eyed male and a white-eyed male. So you would say half of your females will have red, half of them white, half of your males will be red, half of your males will be white, and that's exactly what Thomas Hunt Morgan noticed in his research as well. So that shows that a sex-linked trait is a trait that is a gene that's located, its loci or locus is on the sex chromosome. The X chromosome primarily is the one that we deal with, the Y chromosome being in mammals the one that makes the individual male. If they have a Y chromosome, then they're male, even in the case of mutations that take place. Alright, so let's take this a little bit further then. So apparently you only need one X chromosome. Females, though, we know have two X chromosomes, but whenever we've done studies on them, we notice that the females have two X's, but they do not have twice as much protein as the males have that are on that X gene. So what research has come to show is that one of those X chromosomes will condense into what we call a bar body. In essence, it'll condense down and attach to the nuclear envelope right there on the nucleus, and it won't be used by that cell. That is called dosage compensation. Dosage compensation. The easiest example that we can see with this is the calico cat. The calico cat has both black and orange fur. There's actually an epistasis relationship here too, because there's also a trait for color. So it's you either have white, you'll have white in some areas, you'll have black in some areas, and orange in some areas. The black and orange areas will have the color gene and then express either black or orange. The white areas would be lacking the color gene. Epistasis there. As well as then this example here. So the X with the B gene is black. The X with the O gene is orange. So if you get a female cat that has both the black gene and the orange gene, what happens is you will have patches on that cat of black and patches of orange, depending on which X condenses. Every cell in the body doesn't have to be the same. They can actually be different. You can have some cells that have the black gene expressed, other cells that have the orange gene expressed, depending on which X is condensed. And we see this in all female species of mammals, but it's just most prevalent right there in the calico cat. So then we want to take this further. So now we're looking at a chromosome. We know there's a gene on that chromosome. And we know from meiosis that crossing over takes place where parts of chromosomes will break off and attach to others. So this leads us to another experiment now where we're trying to know, well, what's the distance from one gene to the other on a chromosome? And we did this using a cross here in fruit flies. We took a gray body, gray body is dominant to black body, normal wings is dominant to vestigial wings. So we took a gray body normal wing fruit fly, crossed it with a black body vestigial wing fruit fly. All of the F1s were normal or gray body normal wing. Now, when we do a test cross on this, we would expect a 1 to 1 to 1 to 1 ratio. And we can do a Punnett square to show why that's the case. But for right now, I'm just going to say it should be this. When the experiment was done, we had 405 black vestigial, 415 gray normal, 92 black normal, 88 gray vestigial. That shouldn't be normal. Man, I've messed up all over this one. Gray vestigial. Okay? So when you look at this, you've got the two most common traits were actually what you saw in parents, which would say that these genes, the gene for body color and the gene for wing color, would be on the same chromosome. And the only time you're getting this other one is when these two, whenever you get this alignment, you have crossing over taking place to where you'll have the normal body color, gray, instead of being with the normal wing, will break off and attach to this one over here that's got vestigial wings. It does happen some, but not in the 1 to 1 to 1 to 1 ratio that we would expect if everything was normal. And these were on different chromosomes. So because you get this result, you say, well, these must be on the same chromosome. So now we want to take that a little bit further and say, well, how far are they from each other on the chromosome? So since black vestigial and gray normal are the traits of the parentals, we say that the black normal and the gray vestigial are recombinants. So a new term there you need to know. So in the experiment, I've just totaled this up for you again. 405 normal, 415 normal, 92 recombinants and 88 recombinants. That gives you 1,000 total fruit flies. Okay? So when you add the total recombinants together, 92 plus 88, that's 180. Divide by 1,000, that's 0.18. Multiply by 100 to get percent, that's 18%. We give that a map distance, and there's two different units that they'll use. This is CM, because it's in relation to Morgan, Thomas Hunt Morgan, that did the majority of the research that went into this originally. or we just do map units, MU. Okay? So 18 is the map distance between these two loci, these two genes on that one chromosome. So then we could compare multiple genes. We could see if the distance is greater than 18, then those genes would be closer or further away than these two genes. Or if the distance is smaller. This works up to 50. When you get a 50% here, then those genes are going to act like they're on different chromosomes. Whether they are or not, that distance is going to allow them to act like they're on different chromosomes.